Hello everyone and welcome to episode 5 of Explaining Physics Concepts. In this video we're looking at capacitance. So let's just get right into it. So we're going to start off with what capacitance essentially is. Capacitance, it is defined as the ratio of charge over potential. So this charge, it is charge on one plate. I want you to keep that in mind. Charge on one plate. So capacitance is defined as the ratio of charge over potential or voltage. Now I'm going to take a different route this time to explain you something about capacitance and how capacitance works in parallel and in series. So you must have seen in your previous classes, well, when you have like resistors, in let me bring it down. So let's say you have a cell here and you bring a resistor here, then you have a resistance here, and then you have a resistor here, and then you just go back, right? So and in this part, do you remember how if this when two resistors are in series, the charge, it remains constant and the potential, the volt, that divides. That is to say, if the cell has a potential or voltage of, let's say, 10 volts, right? So here and it's carrying, let's say there's an ammeter here and it is carrying a charge of, let's say, 40 coulombs, right? So here when it comes to resistors, the resistors have, if they have the same resistance, let's say it has a resistance of 2 and then 2R. So here it will get 5 volts, it will get 5 volts as well. So the volt is being divided, but the charge remains constant. This is getting 40 coulomb, this is getting 40 coulomb as well. And if you remember, if you have it, let's say we have these two resistors in parallel to each other. When you have them in parallel and you have 10 volts, they get 10 volts, these get 10 volts, and the charge, it gets divided. So this can get 20 coulomb, this can get 20 coulomb. This is how it used to work. So we're going to take the same understanding towards capacitors as well. Okay. So when it comes to capacitance, in parallel, so let's say, okay, the capacitance sign for capacitance is this. It's not this, it's the same length, 2 dashes. So let's say you have capacitance in parallel. You have this, then you have this, and then you have this. So this right here is C1, this right here is C2, and this right here is C3. So again, so now you know that C equals Q by V, and you have to understand that now that it's in parallel, the voltage remains constant, and let's say there is a charge Q, it gets divided Q1, Q2, Q3. Just what we did, that in parallel the charge gets divided. Now the voltage, it remains constant, right? So we'll write Q equals Q1 plus Q2 plus Q3. This is what we will do, because it gets Q1 plus Q2 plus 3 equals to Q. Now we're going to make Q the subject of this, and we're going to make Q equals CV, right? Now CV equals CV1 plus CV2 plus CV3. And here, what is constant here? The voltage remains constant. You can just cut this and you can say C equals C1 plus C2 plus C3. That's how it, so whatever is getting changed, you make that the subject of equation and then see what else is remaining constant. Let's do this again so you can understand this better. What if you have capacitance in series? So when you talk about capacitance in series, let's say you have this and then you have this. Now here, make a note to yourself. Voltage divides Q constant. So what is changing here? V. That means there was V and then it got divided to V1 and V2, right? That means V equals V1 plus V2. Now if you go back to the formula, C equals QV, since V is changing, we're going to make this the subject and we'll get V equals Q over C. Now Q, we're going to say Q over C equals Q1 over C plus Q2 over C, right? And then you know what remains constant here? Q remains constant, so you can say, you just cut that constant thing out and you get 1 over C equals 1 over C1 plus 1 over C2. So our point here was to get the capacitance, right? How do you find capacitance? So if there's another important thing that I would like you to take note of. Now you see, in parallel, capacitance will just get added as C1 plus C2 plus C3. But in series, the reciprocal of capacitance is added. And this is the opposite of what happens to resistances when in series and parallel. I don't want to confuse you a lot, but what I want to say, do you remember that when you were in parallel, these are resistors. When you are in parallel, you get 1, this is R1, this is R2. So when you have to add the resistances in parallel, you say 1 over R1 plus 1 over R2, right? And then when they were in series, you just did R1 plus R2. So for the capacitance, it's literally the opposite. When you are in parallel, you do C1 plus C2. When you are in series, you do 1 over C1 plus 1 over C2. That is the difference between them, and you just have to understand that. If you know how to derive the formula for C, then it won't be an issue. Now what we're going to do is draw a graph to see the relationship between Q over V. Now C for any capacitor is fixed. C capacitance for any capacitor is fixed, which means if you look at the formula, C equals Q by V, and if I were to remove this equals to sign, I can say that V is directly proportional to Q. Why? Because this C, I just wrote here, C for any capacitor is fixed. That means C here it was a constant, and it was essentially like this, VC equals Q. Since C is a constant, I remove this and I can say V is directly proportional to Q. Now since V is directly proportional to Q, we know how you make graphs for proportionality. They just go straight line through the origin, and that is how you make it, right? Another part, you talk about if I want to find out the area under this graph. Do you remember how area under graph used to be the area of the shape that forms? So this is forming a triangle, right? How do you find the area of triangle? The area of triangle is 1 by 2 into base, which is Q, into height, which is V. So 1 by 2 QV, right? And we can even derive more things from here. QV, okay, since I have C equals Q by V, I can make Q the subject and I can have 1 by 2 CV square, right? I just replace Q with CV. Or I can make V the subject and I can say V is Q by C times Q, and it becomes 1 by 2 Q square over C. So this is how you can get them. Now having done this, what we're going to move on is time constant. Something that confuses a lot of students, and what I'm going to explain it to you in the easiest possible manner. So when a capacitor is discharged, how do you discharge a capacitor? A capacitor is discharged through a resistor. And when a capacitor discharges, everything decreases exponentially. When I say exponentially, you should think of this graph. You start from this and you go. This is what it means exponentially. And let me write something. This is a big important thing. When a capacitor is discharged, voltage, current, and this is charge actually, current and voltage, current and charge decreases exponentially. But the capacitance remains the same. So here, what is decreasing exponentially? Against time. What is decreasing exponentially? I or V or Q. Any of these things, they start decreasing exponentially when the capacitor is discharged. And with this, we come towards time constant. What do we mean by time constant? You must have seen this formula. When you talk about time constant, first, let's define what time constant is. Time constant is the time taken for the capacitor for the capacitor to reduce its ratio of V, Q, or it could be I, any of these things that we mentioned above, to 36.8% of its original value. Now let me explain this to you. I'll explain this through a drawing. You have, first of all, understand that a capacitor is discharged. A capacitor is discharged through a resistor in parallel. So if you have, let's say, a capacitor here, then you need a resistor in parallel to discharge it. Now, Y equals, the formula for time constant is Y equals RC. What is its unit? R is, we know V equals IR, R is V over I. Capacitance is Q over V. We cut this Q over I. What is Q over I? We know I equals Q by T. Q over I is equals to T. T has seconds as its unit. So seconds is the unit for this. So Y, this Y right here is what you call time constant. So all you need to understand is what time constant is, what is its formula, and how is the formula derived, what is its units. And now I'll explain you something Now in this graph, the graph that I just made up, I'll make it again. This is the graph that I made, and I said what it decreases exponentially when the capacitor is discharged, I, current or charge or potential against time. So I would say this is what no, it does not touch the okay. So there is this one formula that just captures this entire graph, that is x equals x naught e raised to the power minus kx. And now this formula is something that you will see a lot in other chapters as well. This is more of a generic formula. Let me break it down. So this is the y-axis, this is the initial value, initial y-axis value, this e is exponential, this negative because it is decreasing graph. Then this x right here is x-axis, and this k right here, the most important thing in this case especially for capacitance, is reciprocal of time constant. Now you'll see this formula so many times, and the k will differ because k is just a constant, but here the k is the reciprocal of time constant. Now if I were to put all things together, so since we know, let's take it with I, we can use anything, we can use I or Q or V. So let's use I equals I naught, so I set initial value, e raised to the power minus, now k is the reciprocal of time constant is y equals RC. So 1 over RC times x, what is on x-axis, t. So the formula becomes I equals I naught e raised to the power minus t over RC, and this is the formula for this. You can do the exact same thing with V. V equals V naught e raised to the power minus t over RC, or you can say Q equals Q naught e raised to the power minus t over RC. So because these three things are the one that decreases exponentially. Now do you see this in this definition I've written, it is a time taken for the capacitor to reduce its value to 36.8. So do you see this number here, 36? Where do you get this number from? Let me explain. That is, let's say you take time constant as 5. Time constant 5, RC 5. So I would say V equals V naught e raised to the power minus 5 over 5, and I get V equals V naught e raised to the power minus 1, right? Now V over V naught, if I bring and make this, if you calculate e raised to the power minus, you get 0.368. 0.368, this is what you get, and if you convert into percentage, you get 36.8%. So essentially 0.36 is the ratio of I or V or Q over I naught or V naught or Q naught, whatever you want to say. That is how you get this. So what do we need to learn in this chapter? We need to understand, number one, what capacitance is. Capacitance is the ratio of this. What are its functions? You can talk about the functions to store electrical energy, to prevent sparks. This is something that is mentioned a lot in past papers. To store electrical energy, to prevent sparks in oscillator circuits, and then talk about how do capacitance looks like in parallel, in series, and then talk about what how does the graph look like, what is time constant, how do you derive time constant, what is its unit, and then you get that formula for that when voltage, when potential or charge or current, when they decrease exponentially, what does the equation look like. So this is it for capacitance. Again, if it sounds too confusing right now, no worries, because we will be doing a lot of past paper questions to understand all of this.